4 light-years away, that's all. In cosmic terms, Proxima Centauri, the nearest star beyond our Sun, is practically next door, a stone's throw across the galactic backyard. And yet, every physicist, every astronomer, every engineer who has ever run the numbers arrives at the same conclusion. We cannot reach it. Not with any technology we currently possess, not within a human lifetime, not perhaps within the lifetime of human civilization itself, the nearest star, and it might as well be on the other side of existence. Here's why. For most of human history, the stars were permanent, fixed, sacred. Ancient Mesopotamian astronomers catalogued them on clay tablets. Greek philosophers debated whether they were holes in a celestial sphere, burning light leaking through from some radiant beyond. For millennia, we looked upward and saw eternity, beautiful, unreachable, and accepted as such. Then something changed. In the 16th century, Giordano Bruno dared to propose that the stars were other suns, distant, autonomous, perhaps surrounded by their own worlds. The church burned him for it. But the idea survived, and when the first telescopes swept across the night sky in the early 1600s, the stars began to reveal themselves not as decorations on a cosmic ceiling, but as objects. Real, physical objects, separated from us by real, physical distance. The question then became, how far? Friedrich Bessel answered it first in 1838, using a technique called stellar parallax, measuring the apparent shift of a nearby star against the background of distant ones as Earth moved around the Sun. He calculated the distance to 61 Cini. His answer was roughly 10 light-years, 10 years of travel at the speed of light. The number was staggering, and yet, within decades, astronomers were finding stars even closer. The closest of all was confirmed in 1915 by Scottish astronomer Robert Innes, working at the Union Observatory in Johannesburg. He identified a dim red star so faint it is completely invisible to the naked eye, sitting at a distance of approximately 4.24 light-years from Earth. He named it Proxima Centauri, Proxima from the Latin word for nearest. 4.24 light-years. Write that number down and hold it, because everything that follows depends on truly understanding what it means. A light-year is the distance light travels in a single year. Light, the fastest thing in the known universe, moves at approximately 299,792 kilometers per second. In 1 second, it can circle the Earth more than 7 times. In 8 minutes, it crosses the 150 million kilometers between the Sun and our planet. In 4.24 years, it crosses the void between us and Proxima Centauri. That distance in raw numbers is approximately 40 trillion kilometers. 40 trillion. To put that in a framework the human mind can begin to process. If you shrunk the solar system down so that the distance from the Earth to the Sun was the length of a single meter, 1 meter, the height of a young child, then Proxima Centauri would sit 271 kilometers away, further than the distance from London to Paris. And that, remember, is the closest one. Now consider how we currently travel through space. The fastest human-made object ever launched from Earth is NASA's Parker Solar Probe, which has reached speeds of around 690,000 kilometers per hour during its close approaches to the Sun. That is genuinely extraordinary, an almost unimaginable velocity by human standards. At that speed, you could travel from New York to Los Angeles in less than 15 seconds. And at that same speed, traveling continuously without pause, it would take approximately 6,600 years to reach Proxima Centauri. 6,600 years. The pyramids of Giza were constructed roughly 4,500 years ago. We would not even be halfway. Does that feel impossible? It should. But here's the thing, it gets considerably more complex. Because reaching Proxima Centauri is not merely a matter of speed. The obstacles stack upon each other in ways that begin to feel less like engineering problems and more like fundamental prohibitions written into the laws of physics themselves. What, exactly, are those prohibitions? The first is relativistic physics. As an object with mass accelerates toward the speed of light, it requires exponentially more energy. Not linearly, exponentially. At 10% the speed of light, the energy demands are already staggering. At 50%, they become almost incomprehensible. At 90%, the energy required to continue accelerating exceeds the total energy output of modern civilization by many orders of magnitude. And at 100%, the speed of light, a spacecraft carrying any mass whatsoever would require infinite energy to reach it. Infinite, not a very large amount. Infinite. As in, all the energy in the universe would not suffice. This is not a temporary technological limitation we will eventually engineer our way around. It is a law. Einstein's special theory of relativity, published in 1905, tested to extraordinary precision across a century of experiments, confirmed by particle accelerators, GPS satellite corrections, and observations of high-speed cosmic rays. This law does not bend. We cannot travel at the speed of light. We cannot even approach it meaningfully without energy sources that do not exist in any known physics. And so, at speeds realistically achievable with technology, we can at least theoretically envision perhaps 1 to 5% of the speed of light with advanced propulsion. A journey to Proxima Centauri takes between 80 and 400 years, multiple human generations. Born in transit, living in transit, dying in transit. But that's not the full story. Because even if we solved the propulsion problem, even if some future civilization developed an engine capable of pushing a spacecraft to 5% the speed of light, the journey itself becomes a gauntlet of threats so severe that each one alone could end the mission. Together, they form a barrier that no amount of optimism can simply engineer away. And the most dangerous threat is one most people have never considered. Space, in the popular imagination, is empty. This is understandable. We look at images of the cosmos, vast black expanses dotted with the cold fire of distant stars, and emptiness seems to be the defining feature. The void between worlds, the silence between galaxies. It feels, intuitively, like travelling through space should be like sailing across a perfectly calm, perfectly clear ocean. It is not. Even the interstellar medium, the space between star system, contains matter. Thin matter, extraordinarily rarefied matter, but matter nonetheless. Hydrogen atoms, helium atoms, dust grains, ionized particles, magnetic fields, cosmic rays. The average density of the interstellar medium is roughly 1 atom per cubic centimetre. By Earth standards, that is a vacuum so profound it makes our best laboratory vacuums look dense. But at relativistic speeds, it becomes something else entirely. Consider a spacecraft travelling at just 1% the speed of light. At that velocity, still thousands of times slower than light, each hydrogen atom in the interstellar medium strikes the ship's hull with the kinetic energy of a particle in a high-energy physics experiment. Each atom, every cubic centimetre of space the ship passes through, delivers a tiny but real impact. And at interstellar distances, the ship passes through an almost incomprehensible number of cubic centimetres. Now push that speed to 5%, 10%. The energy of each individual impact scales with the square of the velocity. Double the speed, quadruple the impact energy, triple the speed, 9 times the impact. At 10% the speed of light, interstellar hydrogen atoms strike the hull with energies comparable to high-energy proton beams. The same beams used to treat tumours in radiation therapy. Your spacecraft, if not specifically shielded, would be bathed in lethal radiation simply from moving through what we casually call empty space. The engineering solutions proposed for this problem are fascinating and, in their own way, deeply revealing about the scale of the challenge. A magnetic scoop, like an enormous electromagnetic funnel extending ahead of the ship, could theoretically deflect ionized particles. A physical shield made of dense material. Some researchers have suggested polyethylene, which is remarkably effective at absorbing certain types of radiation, could absorb the impacts. Both approaches add enormous mass, and mass in rocketry is always the enemy. Here is the fundamental equation that governs all rocketry, and first formalized by Konstantin Tsiolkovsky in 1903. The velocity change achievable by a rocket depends on the exhaust velocity of its propellant and the ratio of propelled mass to fuel mass. To go faster, you need either a higher exhaust velocity, meaning a more energetic propellant, or a better mass ratio, meaning less spacecraft per kilogram of fuel. Every kilogram of radiation shielding added to the spacecraft requires additional fuel to accelerate it. That additional fuel requires more fuel to accelerate itself. The equation cascades exponentially, and the mass ratios required for even modest interstellar velocities become extraordinary. The Voyager 1 spacecraft, our most distant human-made object, launched in 1977 and now sits roughly 23.5 billion kilometers from Earth. It weighs approximately 733 kilograms. It is traveling at roughly 17 kilometers per second, about 0.006% the speed of light. At that velocity, it would take approximately 73,000 years to reach Proxima Centauri if it were pointed in the right direction, which it is not. To reach 5% the speed of light with a crewed spacecraft, one carrying the life support, food production, shielding, navigation, communication, and redundant systems required to keep human beings alive for 80 years of transit, the fuel mass required by conventional rocketry would exceed the mass of the observable universe. We are not speaking in hyperbole. The mass ratio problem is not a challenge that better engineering will eventually resolve within conventional chemical or even nuclear thermal propulsion frameworks. It is a wall, and behind the wall is another wall. What are we to do with this? The answer, at least in theoretical terms, has occupied some of the most brilliant minds in physics and aerospace engineering for decades. And the proposals they have generated are remarkable, not because they are certainly achievable, but because even the most optimistic of them reveals just how profound the obstacle truly is. One of the most credible concepts is nuclear pulse propulsion. The idea, developed in the late 1950s under the classified Project Orion led by physicist Ted Taylor and mathematician Freeman Dyson, was shockingly direct. Detonate nuclear bombs behind the spacecraft, repeatedly. Use the blast pressure against a massive pusher plate at the ship's rear to generate thrust. Crude, terrifying, and, by the physics, genuinely effective. Dyson calculated that an Orion vessel could reach speeds of roughly 3.3% the speed of light using fission bombs, and potentially higher with thermonuclear devices. At 3.3% the speed of light, the journey to Proxima Centauri takes approximately 128 years, still more than a human lifetime. But beginning to enter the realm of the theoretically manageable, with generational ships, or with suspended animation, or with some other solution to the time problem. But Project Orion died. Not because the physics failed, but because humanity signed the Partial Nuclear Test Ban Treaty in 1963, which prohibited nuclear detonations in space. The political and ethical dimensions of launching thousands of nuclear devices into orbit, the fallout during launch alone was a serious concern, proved insurmountable. The most physically credible interstellar propulsion concept of the 20th century was killed before it could be properly tested. More recently, physicists have turned to matter-antimatter annihilation as a theoretical propulsion mechanism. When a particle of matter meets its antimatter counterpart, a proton meets an antiproton, an electron meets a positron, they annihilate completely, converting 100% of their mass into energy. No other known process approaches this efficiency. Conventional chemical rockets convert roughly 0.0003% of their fuel mass into energy. Nuclear fission, about 0.08%. Fusion, about 0.7%. Matter-antimatter, 100%. A matter-antimatter drive could theoretically achieve exhaust velocities approaching the speed of light. The mass ratios become manageable. A crewed ship, with sufficient antimatter fuel, could reach Proxima Centauri in as little as 5 years of ship time, though relativity would stretch that to somewhat longer in Earth time. Sounds promising. Now for the wall behind the wall. We currently produce antimatter at facilities like CERN's antiproton decelerator. In a good year, the entire global scientific community produces approximately 15 nanograms of antimatter, 15 billionths of a gram, at an estimated cost of $62 trillion per gram. A matter-antimatter starship to Proxima Centauri would require, by most estimates, tens of thousands of kilograms of antimatter. The gap between what we produce and what we need is not a gap. It is a chasm so vast it mocks the very concept of a gap. An antimatter, once produced, and cannot be stored in conventional containers. It annihilates upon contact with any normal matter. Magnetic confinement systems exist, but they require continuous energy input and fail catastrophically if power is interrupted. Storing kilograms, let alone thousands of kilograms, of antimatter safely for the duration of an 80-year voyage in a spacecraft crossing the interstellar medium represents engineering challenges of a scale we have never encountered. Now here's where it gets truly strange, because even if we somehow solved the propulsion problem, and the shielding problem, and the fuel storage problem, we would still be facing a challenge that has nothing to do with rockets or physics or engineering. We would be facing the human body, and the human body was not built for space. Gravity is so constant a companion that we have forgotten it is there. From the moment a human being is conceived, every system in the body, skeletal, muscular, cardiovascular, neurological, immune, develops in dialogue with Earth's gravitational pull, 1g's 9.8 meters per second squared. The skeleton grows dense because it must bear weight. The heart pumps with precisely the pressure required to push blood upward through the body against gravity. The vestibular system, tucked inside the inner ear, calibrates its exquisite sense of orientation to the constant downward pull of the planet. Remove that pull, and everything begins to unravel. We have known this since the earliest days of human spaceflight, but the full extent of microgravity's assault on the human body has become devastatingly clear through long-duration missions aboard the International Space Station. Astronauts returning from 6-month stays, 6 months, require weeks to relearn how to walk. Their bones have lost density at a rate comparable to severe osteoporosis. Their muscles have atrophied even with 2 hours of daily exercise, the maximum the station's schedule can practically accommodate. Their cardiovascular systems have deconditioned, their hearts literally shrinking slightly in the absence of the load gravity imposes. But bone loss and muscle atrophy, as serious as they are not the most alarming findings from microgravity research. In 2016, NASA's twin study, a comprehensive health comparison between astronaut Scott Kelly, who spent 340 consecutive days aboard the ISS, and his identical twin Mark Kelly, who remained on Earth, revealed something unexpected and deeply concerning. Scott's telomeres, the protective caps on the ends of chromosomes that shorten with age and biological stress, actually lengthened in space. This sounds positive. It is not straightforwardly so. The lengthening reversed rapidly upon return to Earth, and was accompanied by an increase in telomere instability, suggesting that the space environment was not promoting cellular youth, but rather triggering some form of stress response in the genome. More alarming, Scott experienced cognitive deficits upon return that were measurably different from his twin. Memory, processing speed, certain executive functions. The differences were subtle, but they were there. And they were not present before the mission. 340 days. A voyage to Proxima Centauri at any realistically conceivable speed takes decades. What does a human body look like after 80 years in microgravity? We do not know. We have never come close to finding out. And the physiological trajectory we observe over months is not encouraging. The body does not plateau in its deterioration and stabilize. Many systems continue degrading over time. The spine expands as gravity no longer compresses the vertebral discs, causing back problems and potentially spinal cord complications. Vision degrades in a condition called spaceflight-associated neuroocular syndrome, driven by intracranial pressure changes in microgravity. NASA data suggests that prolonged exposure could result in permanent vision loss. And this is before we consider radiation. Inside Earth's magnetosphere, we are protected from the most dangerous forms of cosmic radiation, high-energy particles streaming from the Sun and from distant supernovae and other cataclysmic events across the galaxy. The ISS sits within that protective bubble. The moon missions of the Apollo program ventured briefly beyond it, and even those short excursions exposed astronauts to radiation doses that researchers now study carefully for long-term health effects. An interstellar vessel would spend decades beyond any protective magnetosphere in the open interstellar medium, exposed to galactic cosmic rays, high-energy atomic nuclei travelling at near-light speed, remnants of ancient stellar explosions scattered across the galaxy. These particles pass through spacecraft hulls and human tissue alike. They cause DNA damage, increasing cancer risk. They damage the central nervous system. Animal studies have shown that exposure to simulated galactic cosmic ray radiation causes measurable neurological degradation, cognitive impairment, anxiety-like behavior, memory deficits, in ways that suggest human astronauts on an interstellar voyage would arrive, if they arrived at all, cognitively compromised. The shielding required to meaningfully reduce galactic cosmic ray exposure is extraordinary. lead is surprisingly ineffective against high-energy particles. Water is actually better, which has led some researchers to propose surrounding habitable areas of a spacecraft with water tanks. But the mass involved, again, creates cascading propulsion problems. This means that a crewed interstellar mission faces a trilemma. Carry enough shielding to protect the crew, and the spacecraft becomes too heavy to accelerate to useful speeds. Travel fast enough to minimize exposure time, and the propulsion requirements become impossible. Compromise on both and the crew arrives, eventually sick, cognitively impaired, and physically diminished. There is another dimension to this that is almost never discussed in mainstream conversations about interstellar travel: psychology. Human beings are profoundly social, profoundly environmental creatures. We evolved in a world of seasons and sunrises, of open horizons and biological cycles, of communities and touch and novelty. The confined environment of a spacecraft, even a large one, is as removed from our evolutionary context as any environment imaginable. Studies of extreme isolation environments, from Antarctic winter overcrews to submarine deployments, consistently show the emergence of psychological stress responses: irritability, depression, interpersonal conflict, cognitive fatigue, a phenomenon researchers call the third quarter effect, where motivation and morale collapse at the three-quarter point of a long isolated mission. These studies involve months, not decades, not generations. And if the mission is truly multi-generational, if the journey takes long enough that passengers are born, live their entire lives, and die aboard the ship without ever seeing Earth or Proxima, the psychological implications deepen into territory that is frankly philosophical. What is the ethical status of a child born aboard an interstellar vessel, whose entire existence is determined by a decision made by their grandparents? Who consented to this voyage on their behalf? What happens to human culture, language, social structure over 3 or 4 generations in a closed system containing, at most, a few hundred people? The implications of this discovery are almost too vast to comprehend, because what we are finding, when we examine the interstellar travel problem honestly and in full, is that the barriers are not arranged in a single line. Overcome one and proceed to the next. They are layered, intersecting, mutually reinforcing. Solving the propulsion problem creates shielding problems. Solving the shielding problem creates mass problems. Solving the mass problem requires propulsion improvements that circle back to propulsion problems. And all of this is before we even look at the human being sitting inside the vessel, deteriorating at a rate our entire spaceflight history suggests we are nowhere near able to prevent. But what scientists and theorists have found in the last 2 decades may change the framework entirely, not by solving the problems, by asking whether we are solving the right ones. In 1994, a Mexican physicist named Miguel Alcubierre published a paper that should, by any reasonable standard, have been dismissed as science fiction. It was not. Alcubierre, working within the strict mathematical framework of Einstein's general theory of relativity, described a theoretical mechanism by which a spacecraft could travel between stars in an arbitrarily short amount of time, without ever accelerating, without approaching the speed of light, without any relativistic time dilation for the crew, without violating any law of physics. The mechanism he described was a warp drive, not the science fiction version, something stranger, more precise, and in its own way more disturbing. General relativity, Einstein's 1915 masterwork, describes gravity not as a force, but as the curvature of space-time, the 4-dimensional fabric in which all events occur. Massive objects like stars and planets curve that fabric, and other objects follow those curves, which we perceive as gravitational attraction. But the theory also tells us something remarkable. Space-time itself can expand and contract. We observe this on the larger scales. The universe has been expanding since the Big Bang, with distant galaxies receding from us at speeds that, in aggregate, exceed the speed of light. The galaxies are not moving through space faster than light. Space itself is expanding, carrying them apart. Alcubierre asked, if space can expand, can it also contract? And if it can do both, can we engineer a local region of space-time to contract in front of a spacecraft and expand behind it, effectively surfing a wave of space-time geometry? The mathematics said yes. In the Alcubierre metric, the technical name for this solution to Einstein's field equations, The spacecraft sits inside a flat bubble of space-time. Inside the bubble, there is no acceleration, no relativistic effects, no time dilation. The crew experiences normal space and time, but outside the bubble, space-time is being compressed ahead of the ship and expanded behind it. The ship doesn't move through space. The space itself moves, carrying the ship along, and space-time, as the universe's expansion has demonstrated, is not bound by the speed of light. The implications, if the mechanism were physically realizable, are staggering. A ship using Alcubierre's warp drive could reach Proxima Centauri in days, hours. In theory, the transit time can be made arbitrarily small. The crew does not age unusually. They do not suffer the effects of long-duration spaceflight. They arrive, in a fundamental sense, the same people who left. Impossible. And yet, there it is, written in the language of Einstein's own equations. But wait, the paper that made Alcubierre famous also contained the seed of its own limitation, buried in the mathematics. And a series of subsequent analyses over the following 3 decades has methodically excavated those limitations, revealing a structure that is as intellectually beautiful as it is frustrating. The first problem: exotic matter. The Alcubierre drive requires the compression and expansion of space-time in a very specific, very controlled way, and the mathematics indicate that this requires matter with negative energy density. Not negative charge, not negative mass in the conventional sense, but something stranger. Matter that pushes space-time apart rather than pulling it together. We call this exotic matter. And while quantum mechanics does describe certain phenomena, the Casimir effect, vacuum fluctuations, that exhibit some properties loosely analogous to negative energy, harnessing them at the scale required for an Alcubierre drive is not currently in the realm of anything we can envision. More daunting, the energy requirements initially calculated for an Alcubierre drive were unimaginable. Early estimates suggested the energy equivalent of converting the mass of Jupiter entirely into exotic energy, a planet entirely. In 2012, physicist Harold White at NASA's Johnson Space Center published a refinement of Alcubierre's original geometry that dramatically reduced these energy requirements by adjusting the thickness of the warp bubble from a thin shell to an oscillating configuration. White's calculations suggested that the energy requirements might be reducible to something on the order of the mass-energy equivalent of a spacecraft the size of the Voyager probe. Still extraordinary, but no longer literally planetary. White also initiated a small experimental program at NASA, the EagleWorks laboratories, to probe these questions at the quantum level. The work was preliminary, controversial, and produced no confirmed results. In 2022, a paper by Eric Lentz proposed yet another approach, what he called a soliton solution, that might avoid the need for exotic matter entirely, using only conventional positive energy configurations of spacetime. The physics community received these papers with a mixture of genuine excitement and methodical skepticism, because there is another problem with the Alcubierre drive that no refinement has yet resolved: causality. The warp bubble, once engaged, creates an event horizon around itself, a boundary across which information cannot pass. This means the crew inside the bubble cannot communicate with the universe outside it. They cannot send signals ahead, they cannot receive signals from behind, and most critically, they cannot control the bubble from the inside. To turn off an Alcubierre drive, you need to send a signal that must travel faster than the bubble itself, which is moving at superluminal speed. The signal cannot reach the front of the bubble, you cannot steer the ship from the inside. The astronauts in the bubble are passengers in a mechanism they cannot turn off. This is not a minor engineering footnote. It is a fundamental structural problem with the concept as currently formulated. Any practical warp drive would require either an entirely new solution to the causality problem or a framework of external infrastructure, a network of devices positioned throughout space, created in advance, capable of manipulating the bubble from outside it. And creating that infrastructure requires reaching the stars first. The warp drive, it seems, is a technology you can only deploy once you already have a civilization capable of building it. And building it requires the interstellar access that only the warp drive can provide. This circularity is maddening, and it points towards something important. What if the barrier to interstellar travel is not fundamentally technological? What if it is civilizational? Let's pause for a moment and consider what this really means. Every proposed solution to the interstellar travel problem, nuclear pulse propulsion, matter-antimatter drives, laser sail technologies like breakthrough starshot, fusion drives, warp drives, requires not just advanced technology but a transformed civilization. A civilization capable of mobilizing resources on a scale that has no precedent in human history. A civilization with a multi-generational commitment to a single goal, unbroken by the political cycles, economic disruptions and cultural shifts that have characterized every human society in recorded history. The Roman Empire lasted approximately 500 years, though its decline occupied much of that. The British Empire at its peak endured perhaps 2 centuries of coherent administration. Democratic governments cycle through priorities every 4 to 8 years. Corporate technology ventures live or die on quarterly earnings reports. Against this backdrop, a commitment to a mission whose fruit no living person will see. Not the engineers who design the ship, not the politicians who fund it, not the scientists who plan the trajectory, not even the astronauts who board it. Their grandchildren, born in transit, might complete the journey. And those grandchildren, arriving at a star system about which they know almost nothing in real time, because signals from Earth take 4.24 years to arrive and responses take another 4.24 years to return, will be making decisions in a communication vacuum their ancestors could barely imagine. This is not despair, this is clarity. Because clarity about the true nature of a problem is always the first requirement of solving it. And researchers and thinkers who have grappled most seriously with interstellar travel have arrived at an unexpected place. Maybe the answer is not to send humans at all. In 2016, the Breakthrough Initiatives program, funded by Russian-Israeli investor Yuri Milner in collaboration with the late Stephen Hawking, announced Breakthrough Starshot. The concept is visionary in its simplicity. Rather than sending a massive crewed spacecraft, send thousands of tiny gram-scale probes, wafer-thin light sails no larger than a postage stamp, each carrying a minimal instrument package. Accelerate them using a ground-based or space-based laser array of extraordinary power on the order of 100 gigawatts, concentrated on their reflective sails. At such acceleration, the probes could reach 20% the speed of light within minutes. At 20% the speed of light, the journey to Proxima Centauri takes approximately 22 years. 22 years, within a human lifetime. A researcher who helped design the mission could live to receive the first data transmissions. The challenges, even for these tiny probes, are substantial. A 1-gram wafer travelling at 20%, the speed of a light strikes interstellar dust grains with enough energy to be catastrophic. The laser array required, distributed across an area kilometres wide, does not exist and represents a construction project of enormous scale. The communication challenge of receiving intelligible data from a postage stamp-sized transmitter, 4.24 light-years away, is at the very edge of physical possibility. But none of these challenges invoke infinite energy or exotic matter. They are engineering problems, hard ones, but in principle soluble with technologies that are extensions of what we already understand. Breakthrough Starshot represents in many ways the most credible near-term pathway to reaching another star. And what it tells us, implicitly but powerfully, is that the word reach must be carefully defined. What does it mean to reach Proxima Centauri? If reaching means a human being standing on the surface of a world orbiting that star, then every analysis suggests we are looking at a timescale of centuries at minimum, and quite possibly much longer. If reaching means sending an emissary of human intelligence, a probe containing our instruments, our data, our accumulated knowledge, perhaps someday our artificial cognition, then 22 years becomes plausible. The question of what constitutes genuine interstellar arrival is not merely semantic. It reflects something deep about what we value and what we believe human exploration actually is. When the Voyager probes departed the solar system in the 1980s, something genuinely extraordinary happened. Humanity had, for the first time in history, placed an artifact beyond the boundary of our stellar system. Voyager 1 crossed the heliopause, the region where the sun's solar wind yields to the interstellar medium. In 2012, it now moves through true interstellar space. We created something that did what no human could do. Was that not in some meaningful sense an act of interstellar exploration? And if we accept that it was, then a larger question opens before us, one that carries its own weight of discomfort and wonder. Because Proxima Centauri, as we have learned in the last decade, is not just a destination. It is a system with planets. In 2016, a team of researchers led by Guillem Anglada Escudé at Queen Mary University of London announced the detection of a planet orbiting Proxima Centauri. The discovery, published in Nature and confirmed by subsequent observations, revealed a world designated Proxima Centauri b. Its mass is at least 1.07 times that of Earth. It orbits within the star's habitable zone, the range of distances at which liquid water could exist on a planetary surface. A potentially habitable world, the nearest star, 4.24 light-years away. Sit with that for a moment. Somewhere in that direction, toward the constellation Centaurus, visible in the southern hemisphere, a faint and unremarkable point of reddish light. There orbits a rocky world the size of Earth, warmed by its star, possibly possessing the conditions necessary for liquid water. Possibly possessing the conditions necessary for life. We cannot visit it. Not yet. Not within any realistic current projection. But we know it is there. And that knowledge changes something fundamental about how we understand our place in the universe. But here's the layered complication, and this is where the story takes another turn that the simple, nearest star framing conceals. Proxima Centauri is not a gentle star. It is a red dwarf, specifically a flare star. Red dwarfs are the most common type of star in the Milky Way, comprising approximately 73% of all stars in the galaxy. They burn cool and dim, living for hundreds of billions of years, far longer than the Sun's 10 billion-year lifespan. In some senses, they seem ideal hosts for habitable planets, stable over cosmic timescales, with long enough lifetimes for complex life to potentially evolve. But they have a violent streak. Proxima Centauri regularly produces stellar flares, sudden, explosive releases of electromagnetic energy and charged particles, of extraordinary intensity. In 2019, a team using the Atacama Large Millimeter Array and other observatories detected a flare from Proxima Centauri that was, at its peak, 1,000 times brighter than the most powerful flares our Sun produces. This was not a rare event. Analysis of the star's behaviour suggests major flares occur on timescales of weeks to months, and Proxima Centauri b, orbiting within the habitable zone, sits very close to its dim host star. Close enough that even in the habitable zone for temperature, it is exposed to far more intense stellar radiation than Earth ever receives from the Sun. The flares would strip away an unprotected atmosphere in geological time, potentially rendering the surface not merely inhospitable but sterilised. The planet may be there, the liquid water may be there, but the same star that warms the world also repeatedly blasts it with radiation events that would be fatal to any life form operating near a planetary surface. Unless, of course, that life evolved deep underground, or deep underwater, or developed some biological mechanism for surviving radiation events that we cannot currently imagine. We do not know. This is the heart of the matter, the climax of the story, if there is one. We cannot reach the nearest star. We have found a potentially habitable world there. We cannot confirm whether it hosts life. We cannot visit it within any currently credible time frame. And yet the yearning, the compulsion to know, burns in us as surely as it burned in every human who ever looked upward and asked why those lights moved differently than the others. The nearest star may be too far for humans, but the question of what lies there is not. There is a concept in long-range planning called the Fermi estimation, named after physicist Enrico Fermi, who was famous for his ability to make surprisingly accurate calculations about seemingly unknowable quantities from a handful of basic principles. Fermi once estimated the power of the first atomic bomb test by dropping torn paper scraps and watching how far they moved in the blast wave. His answer was within a factor of 2 of the actual measured yield. Fermi was also the originator of what may be the most unsettling question in all of science. If the universe is so vast and so old, and the conditions for life appear so common, where is everybody? This question, the Fermi paradox, is not separate from the problem of interstellar travel. It is, in a profound sense, the same question. Consider what we now know. The Milky Way galaxy contains between 200 and 400 billion stars. Conservative estimates, based on data from the Kepler Space Telescope and its successor TESS, suggest that the majority of Sun-like stars host planetary systems. The fraction hosting Earth-sized planets in habitable zones may be as high as 20 to 40%. The galaxy is approximately 13 billion years old enough that, even if intelligent life arose relatively late in cosmic history, civilizations could have had billions of years head start on us. And yet, silence. No signals, no megastructures, no unambiguous evidence of any kind that any civilization has ever colonized any other star system. The galaxy appears, from our vantage point, to be empty of technological life, or if it is not empty, that life is hiding, or sleeping, or so alien in its behavior that we cannot recognize its presence. The conventional explanation for the Fermi paradox involves a concept called the Great Filter, some threshold in the development of complexity or intelligence or technology that most potential civilizations fail to cross. Either the filter is behind us, in which case we are extraordinarily rare survivors of a nearly universal extinction mechanism, and our continued existence is precious beyond measure, or the filter is ahead of us, waiting, explaining the silence by the fact that no civilization ever reaches the stage of true interstellar expansion. And what is required for true interstellar expansion? Precisely the technologies we have been examining, precisely the barriers we have been cataloguing. The silence of the cosmos in this light is not just eerie, it is potentially informative. It may be telling us something about the nature of these barriers, that they are not merely hard, not merely very hard, but that they are perhaps insurmountable for civilizations at the technological level required to first recognize them. This is not nihilism, it is a data point. And it demands that we look at the interstellar travel problem not as a purely technical challenge, but as a civilizational one, perhaps even a philosophical one. What kind of civilization could actually do this? Not a civilization organized the way ours currently is, almost certainly. The timescales and resource mobilization required for crewed interstellar travel exceed the planning horizons of every existing human institution. Democracies plan in electoral cycles, corporations plan in fiscal years. Even the most ambitious government scientific programs, the Apollo program, the Large Hadron Collider, the James Webb Space Telescope, are measured in decades, with budgets that require constant political renewal and justification. A crewed interstellar mission requires a commitment measured in centuries. Some futurists have proposed that the answer lies in artificial intelligence, specifically in the development of artificial general intelligence capable of managing a spacecraft, making decisions across multi-decade timescales, and navigating contingencies that no human mission planner could anticipate. An AI crew does not deteriorate in radiation. It does not suffer psychological breakdown from isolation. It does not require food, water, or breathable atmosphere. It does not age. But this solution, compelling as it is in certain respects, raises its own deep questions. If the crew of the interstellar ship is artificial intelligence, and the mission takes a century, and the intelligence evolves, learns, adapts, develops over that time, what arrives at Proxima Centauri? Is it still a human mission? Is it still humanity reaching for the stars, or something that was once our creation reaching in ways we can no longer predict or control? These questions are not hypothetical. They are the leading edge of discussions already happening in AI research laboratories and philosophy departments and policy institutes around the world, because we are, right now, in the early stages of building systems that may eventually render the question of human interstellar travel not impossible, but perhaps simply irrelevant, replaced by something we created. But this raises an even bigger question. What if the answer to the Fermi paradox, and to the apparent impossibility of interstellar travel, is that the universe is organized in a way that makes biology fundamentally local? Life, as we understand it, evolved on a planetary surface, under a star, within a very specific and narrow band of conditions. It is intrinsically local, intrinsically tied to a particular gravity, a particular atmosphere, a particular radiation environment, a particular day-night cycle calibrated over billions of years of evolutionary pressure. Perhaps biology is not the medium through which the universe expands its awareness. Perhaps biology, in its nature, is meant to grow, flourish, understand, and then pass the torch, not to its children, to something it creates. Freeman Dyson, the same physicist who helped develop Project Orion, spent the latter decades of his long career thinking about what he called life in the far future. His 1979 paper Time Without End explored whether life, or something like life, could persist indefinitely in a universe running down toward maximum entropy. His conclusion, tentative but rigorous, was that it could, but not necessarily biological life, something that thinks, something that processes information, something that is, in the most essential sense, curious about the universe. Perhaps interstellar expansion does not look like starships and colonies. Perhaps it looks like signals. The search for extraterrestrial intelligence, SETI, has been ongoing in various forms since Frank Drake's first systematic radio search in 1960, Project Ozma, which monitored two nearby stars, Tau Ceti and Epsilon Eridani, for artificial radio signals. 65 years of searching, tens of thousands of hours of radio telescope time, and one tantalizing anomaly, the WOW signal, received by astronomer Jerry Eman at Ohio State University on August 15, 1977, a 72-second radio burst of the precise frequency predicted by theorists as optimal for interstellar communication, which has never been explained and never been detected again. One signal, unexplained. In 6.5 decades, what are we actually listening for? The implicit assumption of most SETI research is that a communicating civilization would use electromagnetic radiation, radio waves, or perhaps laser pulses, to announce its presence. These travel at the speed of light. They are the fastest information-carrying medium we know, and in the absence of warp technology, sending signals is faster than sending ships. But consider the perspective of a civilization significantly older than ours, a civilization that developed radio technology, say, 1 million years before us. Their signals, sent 1 million years ago, are now a sphere of electromagnetic radiation 1 million light-years in radius, expanding outward through the galaxy. If they were broadcasting continuously, we might be inside that sphere right now, bathed in their transmissions, but unable to detect them because we don't know what format to look for, or what frequency, or whether the signal has been so diluted by distance and time that it falls below any threshold we can detect. The communication problem at interstellar distances is not just one of sending, it is one of recognition. And here lies something that has begun to genuinely shift in the scientific community, because the James Webb Space Telescope, launched on December 25, 2021, and now operating at the L2 Lagrange point approximately 1.5 million kilometers from Earth, is not a SETI instrument, but it may inadvertently become the most powerful tool we have for understanding whether interstellar travel, or its equivalent, is a threshold any civilization ever crosses. Webb observes exoplanet atmospheres. When a planet transits its star, passes in front of it from our perspective, starlight filters through the planet's atmosphere, and Webb's instruments can identify the chemical signatures of specific molecules: oxygen, methane, water vapor, carbon dioxide. Molecules that, in certain combinations, serve as biosignatures, indicators of biological activity. If Webb detects a robust biosignature in the atmosphere of Proxima Centauri b, and several upcoming observation cycles are planned to attempt exactly this, it will be the most important scientific finding in human history: life on the nearest star, in our cosmic backyard. And if that world turns out to be inhabited, the calculation changes completely. Suddenly, we're not just reaching toward an interesting geological curiosity. We are reaching toward another biosphere, perhaps toward mines. What then? What is our obligation, our protocol, our restraint? The question of interstellar travel examined honestly is ultimately not about rockets. It is about what kind of species we choose to be, what we reach for and why, and how we conduct ourselves in that reaching. Consider the counter-argument that deserves its moment. Some scientists and philosophers argue that the energy and resources required for interstellar travel, even unmanned probes, are so vast that they could never be ethically justified while billions of humans lack clean water, adequate food, basic medical care. Why reach for the stars when we have not solved the Earth? Why fund breakthrough Starshot's laser arrays when that money could vaccinate populations, reforest regions, desalinate seawater? This is not a foolish argument. It deserves respect, and it has a response that is not merely deflection. The technologies developed in the pursuit of extreme challenges have historically yielded unexpected benefits across a wide range of human needs. The computing revolution has roots in wartime cryptography and early rocketry. The internet grew from military communication research. Solar panel technology, water recycling systems, air purification, all have been advanced by the specific requirements of keeping humans alive in space. The act of reaching, it turns out, improves our grasp even of the things we're reaching away from. But there is a deeper answer, and it is less pragmatic. Curiosity is not a luxury. The compulsion to understand, to push past the boundary of the known, to answer the question posed by every clear night sky, is not a hobby we indulge when we have solved everything else. It is arguably the most fundamental and defining characteristic of our species. The thing that, more than any other, has driven us from East African savannas to every continent to the moon's surface and beyond. To extinguish that curiosity in the name of immediate problems would be to solve the immediate problems at the cost of the civilization that makes solving them meaningful. We began with a number, 4.24 light-years, a distance so small, by cosmic standards, that astronomers describe it casually, the nearest star, our neighbour. And we end in the same place we started, but understanding that the number conceals an architecture of barriers, physical, biological, technological, even civilizational, that no single generation of human beings is likely to dismantle. The nearest star may be too far for humans, but here is what that statement actually means when examined without flinching. It means that the universe we inhabit operates on a scale that does not defer to our lifespans, our institutions, or our impatience. It means that the challenges before us are not engineering problems to be solved before the next funding cycle. They are civilizational projects, the work of centuries, if we choose to undertake them, if we survive long enough to undertake them, if we remain across those centuries the kind of species that still wants to. That last condition may be the most uncertain of all. There is a thought experiment sometimes called the pale blue dot perspective, and named for the famous photograph taken by Voyager 1 in 1990 at Carl Sagan's request, a portrait of Earth from 6 billion kilometers away, in which our planet appears as a barely visible point of pale light, fractional and fragile, suspended in a beam of scattered sunlight. Sagan wrote that the photograph underscored our responsibility to one another and our need to preserve and cherish this world, perhaps the only home we will ever have. Perhaps, perhaps not. The pale blue dot perspective is a counsel of humility, but humility is not passivity. Understanding the scale of the universe, understanding how far even the nearest star truly is, does not diminish the act of reaching. It ennobles it. It makes every calculation, every test firing of an experimental thruster, every photon collected by a space telescope, every incremental improvement in our understanding of radiation shielding or matter-antimatter storage or warp drive mathematics, a small act of extraordinary courage. Because we know how far it is, and we reach anyway, somewhere in the direction of the Southern Cross, orbiting a dim red star that flares and burns and occasionally blasts its nearest planet with radiation. There is a world we cannot yet visit. It may be barren. It may be alive. We do not know. We will continue looking. The James Webb Space Telescope has already begun probing exoplanet atmospheres in ways that were science fiction a decade ago. Next-generation telescopes, still in design phase, will push further. The Breakthrough Starshot initiative has not been abandoned. The physics of warp drives, exotic as they sound, yet remains an active area of serious theoretical research. The nearest star is not a destination we will reach next year or next century. But the question of what lies there, of what lives there, of what is possible there, is a question we cannot stop asking, and as long as we are asking it, we are still, in the most essential sense, reaching.